All right, so thanks for coming to the WebGPU discussion of BlinkOn 20. My name is Ken. I am the team manager of WebGPU at Google, and I see a lot of colleagues from Microsoft who've contributed a lot, and other folks as well. So thanks for your contributions. Thanks for coming, and this will be very interactive. So don't expect a lot of pre-canned content. So as most of you probably know, WebGPU is a GPU accelerated graphics and compute API, which is designed as the successor to WebGL. It follows the designs of modern graphics APIs like D3, D12, Metal, and Vulkan in alphabetical order, no favoritism here, meaning that it's a fairly stateless API and doesn't have this problem where you have this global OpenGL context state with lots of things interfering with each other. WebGPU has actually already seen major uptake in the web AI ecosystem, in case you didn't know. Microsoft's invested quite a lot in the Onyx runtime, and Sushant here optimized that considerably with the new primitives that were recently added to WebGPU. And Hugging Face has picked this up and is using it to serve up many models on their website to run client-side in the browser, which is very cool, and there's just a huge amount of excitement in this ecosystem. In the graphics domain, there's a lot of ongoing work. I just tossed a few links in here. You can get to this slide deck already. By the way, it's on bit.ly, BlinkOn 20 WebGPU discussion. And I'll just show a couple of demos as motivating use cases. So here are Three.js's WebGPU samples. Here's some animation retargeting going on between different 3D models. They have a bunch of compute examples here. If somebody wouldn't mind keeping doing this. So here's, flock of birds going. The frame rate's terrible up here. It's much better locally. You can try this on your own machine. Here's deformation of geometry in a compute shader. There's tons of stuff that you can do, and basically all modern rendering techniques require a little bit of compute at least, and then rendering the results. And WebGPU finally allows us on the web to implement these kinds of techniques. Again, let me just highlight one other thing. So Unity and Chrome have been collaborating for a while now, a couple of years, on bringing WebGPU to their engine, and now finally you can compile your Unity project to a WebAssembly module that uses WebGPU and elevates the feature set. It basically gets you all the desktop class rendering techniques that weren't available in WebGL because the API was just too limiting, and now you can do them on the web. So let me just let me show you one. Let's see, one other example. This one's pretty neat. Let's see if this works. Look, Ma, it's really 3D.
Nice. It's not a video.
Not a video?
Not a video. No. You can come interact with it here. So this is Unity's visual effects editor, VFX editor. Again, finally available on the web because compute shaders are in WebGPU. All of these particle simulations are run on the GPU and then rendered directly from the buffers that were computed. So we breathe a sigh of relief as finally we've gotten out of the pit of despair of the OpenGL ecosystem evolution or lack thereof, and now we're finally on modern APIs. So WebGPU is currently shipping in both Chrome and Edge, and we are hoping for shipments in Firefox and Safari, I would say early in 2025. I'm not promising anything for anybody else, but we, like all the browser vendors, are sitting in the WebGPU working group meetings basically every week. And there's been a lot of progress in all the other implementations. And again, we're hoping that these dovetail to shipments in all browsers on all platforms. So what are some of the current major ongoing projects that are, some of which are wrapping up? WebGPU compatibility mode, which I should have hyperlinked here. I'll do that later. It basically subsets the WebGPU API in a way that still gets you compute shaders, no doubt. That's the #1 most important feature. But it does cut down some limits and put some constraints on, like you have to tell it what kind of texture you're creating at the beginning of time. And there's some more severe ones too, but it does let you basically reach all WebGL2 capable devices with the WebGPU API. And so on the Chrome team, we're hoping that people will target this mode by default as they develop their apps, because that means it'll run on a long tail of like Android and Chrome OS devices in particular, which Google has obviously a vested interest in. But I think it's also useful for, say, Microsoft colleagues, because it'll also run on a bunch of older Windows devices that otherwise wouldn't get WebGPU. So anyway, this project is wrapping up. We said it was going to take 1 year. It took 2. Whereas Rick Byers, I'm terrible at engineering estimates, but we all thought it was going to take a year, and it just took. That's how long it took. But it's really coming to a conclusion now. A good conclusion that 3 engineers on Chrome contributed mightily to. WebGPU.h. This is a multi-vendor C and C++ API that lets you do it, WebGPU from native code. You can build your app outside the browser, and then you just recompile with the mscripten toolchain, and it runs in the browser. That's how it works. That's simple. No kidding, Ma. This really works. Privately here among us, when we were collaborating with Unity folks, they ran into like an early blank screen bug, which is the classic computer graphics bug. In case you didn't know, you get a blank screen. It's like, why? Are all the lights out? Is the camera pointing the wrong direction? Whatever. But they couldn't figure it out, and the debugging story for mscripten binaries was not great in the browser, at least at the time. So they invested the time to use this native API with Google's native WebGPU implementation. They compiled it outside the browser on Windows, debugged that binary with Visual Studio, found their WebGPU usage errors, fixed them, and then they recompiled with mscripten and just worked on the web. So there's a nice, tooling story for everybody where you can actually, debug where it's best for you with this API, just like you could with OpenGL, but actually it's more portable because OpenGL was a nightmare to debug between like Windows and Linux, for example. But this API, you can switch between implementations. You could go use Mozilla's Rust-based implementation or Google's, separately from the browser. Another major project that's made a lot of great progress and is kind of wrapping up is Tints IR. So this is a new shader compiler backend in Chromium. The first one was designed for like ease of understanding how correct the transformations were of the shader as it goes down to, D3D, like HLSL, Direct 3D shading language, or Metal shading language, or SpearV for Vulkan. And yet it wasn't really efficient, and there were some order n squared algorithms in there, and people complained that WebGPU shader compilation was too slow. Anyway, this project solves this problem by giving the shader compiler a better mutable intermediate representation. Other projects, subgroup support, allowing different lanes, different threads to cooperate in computing certain results. That already shipped actually fully, and subgroup matrices are finishing up and I think going to origin trial. And again, our colleagues at Microsoft, I think, have used them to good effect.
Yep.
All right. So you're going to see a 3 to 4x, speed up of stuff as you use this in the right way for your AI model evaluation. The team's working on more enhanced fuzzers to be able to fuzz the intermediate representation of the compiler more deeply than you could from source. We're collaborating with the Android team on doing Kotlin bindings for WebGPU, so that at the Java level, at the Java virtual machine level anyway on Android, you'd be able to use this as a first-class application development graphics API, and there's more. So that's what I've got. The roadmap for 2025 is pretty robust, and some of the stuff ongoing is, for example, assisting with Skia's new Graphite backend, which will be hosted on top of Dawn, the WebGPU native implementation inside Chrome. That's how we're getting platform compatibility. And inside Chrome's graphics stack, we're eliminating the OpenGL ES abstractions that have been the lingua franca of how the browser talked about rendering, and we're ditching those and we're going and using Dawn, like WebGPU.h abstractions instead. This is a major positive step forward. I cannot tell you the number of times we had like OpenGL state issues between Skia's Ganesh backend and the outside world, and somebody set one state bit and it just broke rendering. Like you could use WebGL2 to turn on a state bit, and that leaked into Ganesh and broke all the browser's rendering. So many of these bugs, and these are now gone with the new stateless API. So, you know, if folks are interested in helping with that, there's plenty of like Chromium level work to be done, and we can absolutely, you know, share it, mentor people, and contributions would be very, very welcome. Another one is this concept of bindless graphics, which has been in the industry for a while and basically lets you pass GPU addresses into shaders. It's an absolute necessity for advanced rendering algorithms and totally unsafe for use on the web, but our task is we have to make this safe and we have to expose this functionality, because without it, you can't do the leading edge techniques like nanite. You have to have all the textures available to you all at once in the scene. And we will get there. Corentin has written a fantastic explainer and has figured out how to lower this down to the primitives on each platform safely. So again, if you wanted to collaborate on that, we'd be more than happy to. Maybe we could share the load across different platforms to implement it. Better support for unified memory architecture GPUs. Like every mobile GPU is UMA, and you want to eliminate copies on the way to the GPU. So there's a new API proposal for this. There's some really cool stuff we can do with this now, where you could actually memory map the GPU buffer all the way to the renderer process, so that JavaScript or WebAssembly can write values that the GPU can pick up. I don't know, I've been working in this space for a while, but even back in Java days, and the production of values on the CPU that the GPU can see was like a major bottleneck for any like high level language like Java, JavaScript, etc. And now we're really reaching the performance frontiers with the sandbox on, which is really cool. You know, you'll actually have sandboxed and safe race-free access to the GPU memory, and be able to like raise the performance ceiling of your applications with this. And finally, you know, there's a lot more shading language evolution and built-in primitives that we intend to add. We're more than happy to receive new use cases from anybody and everybody as you have applications that you know, oh yeah, okay, there's this feature in Vulkan or Direct3D 12 that isn't exposed in WebGPU. Okay, can we abstract over it? How would we, you know, expose it safely to the web and then get it up there? And we're working with partners on some of these already that we know need to be done. Like, can you index a uint 8 array into a texture? You know, that is one thing that's needed for image processing in compute, and so we're gonna probably be adding that. So anyway, this is the state of the API today and a little bit about where we're headed in 2025. And I'd basically like to open up the floor. Anybody have, you know, uses for this API, you know, questions about its implementation, direction, suggestions? Please, Sunny.
Yeah, just wanted to mention that Skia Graphite is now shipping on Apple Silicon Macs. So if you're running an Apple Silicon Mac, you're most likely using it on the latest like Chrome stable. So you are using Dawn all the time. You're using GPU.
Yes, it's really a huge step. We've been trying it tangentially on the WebGL side to get onto the Angle library everywhere, because that is like a really robust implementation of the OpenGLES API, the WebGL semantics. And Android was the last bastion. We can't ship on Android. We've tried so many times. And when you slot in Angle as the OpenGLES implementation underneath Skia's Ganesh backend, it just adds some performance overhead that we haven't been able to get around yet. So when we ship Graphite finally on Android, that eliminates OpenGL from the equation on the Chrome rendering side, and then we're finally just going to like flip the switch, and WebGL is universally, you know, behaving everywhere. So I'm personally very excited about this.
Question, Ken. So WebGL 1 and 2 JavaScript clients, what is like the future roadmap for them to have a JavaScript translation library to WebGPU?
Well, a couple of things. So first of all, they're never going to go away, right?
Wow.
We're not going to take them out of the web platform. A JavaScript level translation layer is probably not practical. I don't think we're going to be able to write all the needed bookkeeping in JS and have it be that performance. But there is an ongoing project that we can talk about where there's a thought to build a WebGPU backend for Angle. Okay, now that doesn't blow your mind. I don't know what we're. But basically, so the OpenGLES implementation in Chrome could then talk to Dawn, the WebGPU implementation, to do buffer mapping, and you have to do some like shadowing of buffer contents in order to maintain OpenGL semantics, where WebGPU semantics are very different, more explicit. So you do that bookkeeping inside Angle, but use the WebGPU implementation. Now, if you do that, all right, all of a sudden, Angle is just another mscript compilable library conceptually.
Yeah.
And you can just move it into the renderer process. So a whole bunch of code that implements WebGL could get out of the secure boundary in the GPU process and get into the uncrusted render process, which is a win from a security standpoint.
So Angle and the state tracking goes into the render. You go via the pass-through command buffer.
You don't even need to.
You don't even need
that. That's gone then, because you're talking the Dawn wire protocol between the renderer and the
Dawn wire done in the GPU process over whatever Vulkan or Metal or D3, D12 and everything.
Or Angle.
Yeah.
Or Angle. Or Angle again.
Too many times Angle.
Right. It's one of those metacircular problems, but yeah.
Okay. And all that in 2025.
No, we're not promising that in 2025. Yeah. Other thoughts? Anybody doing? Oh, please, Ryan.
So I know for WebGL, I believe basically everyone's using Angle. All browsers are using Angle. Is that true?
No, that's not quite.
No, not quite true.
Yeah. So Firefox still does their own very, very manual WebGL implementation. They use Angle on Windows because translating to D3D11 is a really nasty problem. So they just sort of picked up that implementation and used it. But their code is like talking OpenGLES in their GPU process. They do their validation pretty manually. In Blink, years ago, there was an attempt to build WebGL version 2 in basically the renderer process. And there's a ton of bookkeeping that you have to do. Like for every texture object, an image on the GPU, you basically have to track every bitmap level and like what format is it and what's its size and is that compatible with non-power of 2 filtering and blah, blah, blah. It's a huge pain. And so basically we decided, okay, let's just give Angle that responsibility. And so that's the way that we've taken, by and large, in Chromium. It turns out that Apple picked up the same approach. We worked with them back starting, I think, 2019, 2020. They've fully integrated Angle into WebKit, and that's how they shipped WebGL 2. So
yes. So again, I think the question is: do we have similar things happening for WebGPU, or are we getting independent, fully independent implementation?
That's a really good question. No, there actually are fully independent implementations. So in WebKit, Apple has built their own handcrafted metal backend for it. In Firefox, it's WGPU and WGPU RS. It's a Rust-based implementation of first lower level concepts and then one layer that provides the WebGPU API. And if there's any Igalia folks here, I kind of gather that the non-Apple ports of WebKit are actually using Dawn. Can anybody confirm that?
No Italians.
No Italians here? Okay, I kind of heard that they wanted to ship WebGPU in the WebKit ports to GTK or Windows. And the path of least resistance was just take Dawn and put it into WebKit and use that as the WebGPU implementation. So I think that actually you will see that happening.
With subgroup matrices, is there a plan for doing a fallback over subgroups while Windows gets drivers that support subgroup matrices all the way? Or is that something you just want to do pass through if the current machine supports subgroup matrices, you expose it or you don't?
That's a good question. I don't know whether we've talked about kind of polyfilling the implementation inside Tint.
Yeah.
But I mean, we could discuss it for sure. And if it seems that like the shader compiler could maybe do a better job than you could do at the user level, I think certainly would be amenable to putting such an implementation in. But the challenge is you don't want to put a suboptimal implementation and advertise that to developers, especially when they don't know whether they're really using the hardware support.
Yes.
So that's generally why these things are phrased as optional features. And we've been bitten by this before, like compressed texture support, for example. It turns out that developers used that in order to get the 4x or 8x space savings in video memory. And in order to claim that angle was conformance, it was actually decompressing certain texture formats, and developers noticed it. So we don't want to polyfill this stuff too aggressively.
DP4A has the similar problem on Mac where it's not performant, and I think you exposed that as feature support. Though DP4A works, DP4A is not performant on Mac.
Okay, interesting. I didn't know that.
I just want to know about this abstraction layers performance cost. Like I know WebGPU kind of abstracts the lower level metal or D3, D12 or Vulkan. But if Skia Graphite would have done direct call to Vulkans and versus via the Dawn layer, is there some kind of balances that is done or is it measured? For example, Skia Ganesh was like direct call to GL or Vulkan versus Skia Ganesh has to go through this Skia Graphite has to go through an intermediate Dawn and then reach the final VK calls, for example.
So a lot of performance measurement has been done, yes. And there are inevitably some performance overheads associated with using Dawn, but none that seem to us intractable. They basically are like, yeah, we know that that's inefficient and we're going to go and optimize it. And we expect that to fall off the profile, bit by bit. Our colleague Brandon Jones, the WebXR expert, has recently been doing this, and he profiled a bunch of stuff. It's like, bit sets are expensive. They're all over the Dawn profile. Why is that? And it's because an old implementation of those were picked up out of Angle a long time ago. The Angle ones got optimized, the Dawn ones didn't, and so he's busy, optimizing that and expects like all of that to fall off the profile. We're going to do the same thing again, I think, for it's during render pass encoding. There's like a bind group validation phase, I think, and it does something where it wants to find out if the thing's in the hash table already. So it makes the object, and then it hashes the object. And it goes and sees, hey, is that already in the hash table? And if it is, it goes, picks up the other object and deletes this one. All right, so I think we'll optimize that away. And there's probably a bunch more. So I think we'll just go step by step. Use our, thinking models to go step by step in this process and knock things off the profile until things are sort of uniformly in good shape. But there are also, by the way, some micro benchmarks and web pages that render faster with Graphite's Dawn backend than it do with the direct to Vulkan backend. And that's because some of the bookkeeping was easier to do, like at the abstraction layer, and hard to get right, 100% right and efficient at the application layer. So like eliminating some of those concerns, it turns out that the stuff actually runs faster.
Okay, yep, sounds good.
Yeah, and just to add some nuance there, like you probably don't want a comparison between Graphite on Dawn and Ganesh on Vulkan. You want a comparison between Graphite on Dawn and Graphite on native Vulkan.
Yes,
right?
that's what I'm
That's what
talking
you want to do, because Graphite and Ganesh use completely different
isolation strategy. Yeah.
You can't really compare them that way.
Yeah, I was assuming that you were talking about Graphite Dawn VK versus Graphite VK.
Yeah, that
right.
kind of the main thing.
Right, and that has been measured, and a lot of work is going into that in service of shipping Graphite on Vulkan-based platforms.
Okay.
What sort of asks are the people doing like AI workloads like us? Like, are they asking for the FP 8 support and crazy stuff like that? but they are. Okay.
Yeah, I mean, absolutely. So going back a slide, right? That's in here.
Well,
The
it's in
subgroups and subgroup matrices, like that was done in service of the AI workloads.
Yeah.
There are a bunch of the smaller data types have already shipped. I just took a peek at some slides from a different talk and didn't copy it all in here, but bfloat 16 or something is not shipped yet.
Yeah.
So that will help some AI workloads.
Yeah, that makes sense. But not down to like the it's only a handful of features that's for like ethics or anything like that. Yeah.
Well, not yet,
yet,
but
but
I would
eventually.
anticipate that as those become more
Yeah,
prevalent,
yeah.
that it makes sense to expose optional features targeting them. Also, there's some cool extensions that have been developed and picked up, like NVIDIA specific stuff that DirectML, for example, was able to pick up in their implementation because they knew that
This looks like that thing.
more that it wasn't standardized, but still the private implementation of Windows's machine learning evaluation engine could talk to it. If you want something to show up in WebGPU, it's got to be standardized. In like SpearV, that's the instruction set for Vulkan, HLSL, etc. And so we continue to urge all the GPU vendors to please standardize their stuff. And I make a plea here to any operating system vendors, please push your GPU vendors to do that, at least in HLSL, get it started, get the process started, and then they'll be more motivated to do it on other platforms as well.
In Phyllis's talk on WebNN earlier, she mentioned that one of the things that we've got coming up is deeper ties between WebNN and WebGPU. That's always weird when there's these two entirely independent web APIs that suddenly know about each other. Are there any other point-to-point integrations between WebGPU and other webs?
Yeah, so one that's I think we talked about is 2D canvas interoperability. So a zero copy way of taking the 2D canvas rendered frame buffer and like giving it to WebGPU so you can run some shaders and draw some geometry on it and then hand it back zero copy as well. And the idea is that you get extensibility of 2D canvas in a portable way among browsers without having to keep, putting new features into 2D canvas and getting pushback from vendors. Oh, well, this isn't supported in core graphics, so we can't add it to the 2D canvas spec. But if you could just implement it in WebGPU, then yeah, you could, as long as they implement the interoperability API. So that's a good question, and that's another point-to-point interaction that we're talking about.
There's also the WASM one, right? WebGPU and WASM that are not interoperable exactly, but like shared memory exploration.
Yeah, so there's the mmap proposal in WebAssembly is another really cool one. So this, like up to this point, if you want to memory map one of the WebGPU buffers and get it accessible to mscript and to the WebAssembly environment, you have to make a copy in both directions, and it's horrible. So now you can take a segment of memory externally to the WASM heap and memory map it into the middle of the linear heap. And this is also really cool, by the way, because now you can get C++ code compiled running in the browser, sandboxed, talking directly with no copies to the GPU memory and basically writing geometry that can then be consumed. And that's really cool. If you need more motivation on why it's cool, I'll be happy to talk with you after the talk. But yeah, that's also a game changer. And I hope that we can get that motivated and shipped soon.
I guess another one is WebXR and WebGPU.
Yes, that is an excellent point. So Brandon Jones just got the initial prototype of the WebXR WebGPU integration working. And you can try it now. It's out there. You can turn on feature flags and test it. And it again is very cool because it lets you do much more advanced and fast rendering that you could do with WebGL. Yeah, geez, as we keep talking, the more point-to-point interactions.
And video import, right? WebGPU is the only API which gets zero copy video import.
Yeah, that's exactly.
WebGL doesn't get it.
Right. So that's one that's been in there, in the spec since the beginning. And it was a strong desire. We tried to do this in WebGL and it was just way too complicated. It ended up like having to surface all the video formats up to the end user, and that was a no-no. So in WebGPU, yeah, you can basically zero copy, bring in video frames and HTML video elements process them, render them, and Google Meet is going to end up using this when they ship a WebGPU backend. Yeah. So yeah, there's a lot of good integrations between WebGPU and the surrounding platforms. So thank you for bringing it up. Yep.
There's one thing with WebGPU canvas, they were promotable to overlays. How is it with WebGPU? How
In
will it?
WebGL, it was
Yeah.
possible.
Yeah.
Same thing. Same thing. They're overlayable.
Okay.
The synchronize
You don't
reviews, right?
No, you don't need that.
Desynchronize doesn't work yet. Like it doesn't do the fancy things on like Windows at least.
Yeah, no, I don't think it does. I think it's basically ignored. And I don't know whether we really need to do that. I don't know. It was done for one specific handwriting use case and had a lot of.
It proved very popular.
Yeah.
Wonder if it's gonna be needed again.
Okay. We can discuss.
Ideally not.
Does WebGPU has like this same Vulkan validation layer stuff for validation? Are we missing out on that if somebody is trying to validate their WebGPU calls?
They're not used by default, but you can turn them on.
Okay.
So if you need deeper, understanding of why something failed, yeah, you can definitely turn on the Vulkan validation layers in the GPU process. But the WebGPU validation, make sure that the shape of the data coming in conforms to the spec, is very robust. And in Chrome, Brandon Jones in particular did a lot of work making those error messages very comprehensive, and even talking about like causes of why something happened. I don't know how he recorded this, but at the bottom level, when the error happens, it's like, and this happened because you had this, thing here. And the reason
They're quite verbose. Yeah. Anyway, Vulkan validation is also quite verbose. Sometimes extra verbose confuses you. And then the driver person say, no, you can't just ignore that.
Right. Otherwise, you'll crash.
But thanks, yeah.
So, other thoughts? Anybody using this stuff in production?
You mentioned bindless, useful for nanite and those kind of upcoming techniques. Do you have a list internally of like other techniques that are coming? I just know NVIDIA is working on like neural texturing, and do you know if that's going to require newer stuff from WebGPU, or that's going to be available? That kind of, is there still stuff you can't do on WebGPU, but you will be able to do on more native APIs?
I mean, for sure, yeah. There's like ray tracing hasn't been abstracted in an API independent manner yet. I think we don't know whether it can be, because the shaders are like different enough between APIs that it's not 100% clear whether you can abstract among them cleanly. But neural texturing, I don't know what the primitives are that let you do that. If you have more insight and can send us some pointers, happy to learn. But we want to keep adding more primitives to vertex, fragments, and compute shaders, basically, to let you access all hardware functionality. And there's certainly ways to go.
You mentioned that the Unity folks sort of recompiled their app into native to debug it. Is there plans to have deeper DevTools integration with WebGPU debugging, like a render doc style situation?
Good question. Two of the engineers on Chrome's WebGPU team have been super interested in the debugging problem for a while. And the plan is, as they wrap up their work on compatibility mode, they're going to take a look at the problem space. Now, we don't want to get in the business of writing a whole graphics debugger, because actually it's very difficult to build that on top of a totally platform abstraction. What are you going to do? If you actually could hook into the native API, then you got to backmap everything up to Wigzil. The one current thought is, let them do a very deep record and replay for like all Dawn apps, both inside and outside of the browser. I think that'll help with graphite debugging as well in the grand scheme of things. And then use that, and you could basically replay it into render doc outside the browser and use all or Pix and whatever else you got, and use the platform's best of breed graphics debugging tools, but at least you can reliably capture the WebGPU command stream. So I'd really like to see that, because we've had a lot of bad experiences having to debug Chrome's OpenGLES-based graphics stack over the years. And it's like, I see a rendering artifact, how am I going to get it? Well, I can just go recompile the browser and instrument some code right in the middle where I think the bug is. And yep, it was transparent pixel. That's why you see the flicker. We don't want to have to do that ever again. All right, well, we're basically out of time. So thanks everybody for coming and
Thanks.
stay in touch.